This video is brought to you by mywayteaching.com.
So now we consider two cells which are connected in series. So this rule for series combination we can extend to any number of cells. So the first thing is the equivalent EMF of a series combination of n cells is just the sum of their individual EMFs. Okay, if you want to calculate the equivalent resistance of n cells which are connected in series, it is just the sum of their individual EMFs. So this is the first rule. Okay, and the second one is the equivalent internal resistance of a series combination of n cells. Again, it is sum of their internal resistance. So as you saw in this case, similarly, the equivalent resistance of n cells which are connected in series is the sum of n internal resistance, individual resistance, isn't it? This is so when the current leaves each cell from a positive electrode. If in combination the current leaves any cell from the negative electrode, then the EMF of the cell enters the expression of EMF equivalent with the negative sign. As I said, if two negatives are connected end to end, then the equivalent result EMF will be epsilon 1 minus EMF 1 minus EMF 2, isn't it? Yes. That is the only difference. Now you consider when two cells are connected in parallel, what happens? See, I1 and I2 are the currents leaving the positive electrodes of the cells. At the point B1, I1 and I2, as you can see at the point B1, I1 and I2 flow in, whereas current I flows out. So this current I is equal to I1 plus I2. So let V of B1 and V of B2 be the potentials at B1 and B2 respectively. Then, considering the first cell, the potential difference across its terminals is given by V of B1 minus V of B2. Then we can write V is equal to V of B1 minus V of B2. So points B1 and B2 are connected exactly similar to the second cell. So when we consider the second cell, we can write the same expression. The voltage remains the same. Isn't it? Then we can write I is equal to I1 plus I2. This we know. So if you use the equations of voltage, we can replace this current equation. So V is given by this equation. So if you want to replace the total combination by a single cell, as you can see in this figure, between B1 and B2, an equivalent EMF and an internal resistance R equivalent is considered. So then we can write V is equal to EMF equivalent minus I R equivalent. So this EMF equivalent is equal to, just now we have written the complete equation. And this R equivalent is given by so this will take the form of this. So here in this figure you can see two positive terminals are joined together and two negative terminals are joined together, isn't it? So that currents I1 and I2 flow out of positive terminals. If the negative terminal of the second, if it is connected to the positive terminal of the first, then we'll just, in these equations, this epsilon 2 will replace it with minus EMF2. Okay, that is the only difference. So if there are n cells of EMF 1 to n, and if their internal resistance is R1 up to Rn, which are connected in parallel, then we can write the equivalent EMF as, first we can write the equivalent resistance as 1 by R equivalent is equal to 1 by R1 plus 1 by R2 up to 1 by Rn, and equivalent EMF equivalent by R equivalent, like this, we can represent it with these equations. Okay, this is very simple. Now let us study about Kirchhoff's rules. Electric circuits generally consist of a number of resistors and cells which are interconnected, sometimes in a complicated way, isn't it? Yes. So the formulae we have derived earlier for series and even for parallel combination of resistance are not always sufficient to determine all the currents and potential differences in the circuit. So even though we have the formula, it's really difficult in some of the complicated circuits to determine the overall potential difference or the overall current in a circuit. So in order to simplify these circuits, we have these Kirchhoff rules, and these rules are very useful for the analysis of electric circuits. Okay. So you know what we'll do in this. If you have given with a circuit, then we stand by labeling the currents in each resistor by a symbol, say I, and a directed arrow to indicate that a current I flows along the resistor in the direction indicated. So if this is a simple circuit, if you consider something like this, then what we'll do, we'll label the current I with an arrow in each resistors. Okay, we label it. If I turns out to be negative, the current actually flows in a direction opposite to that arrow. Similarly, for each source, whether it's cell or some other source of electrical power, the positive and negative electrodes are labeled as well as a directed arrow with a symbol for the current flowing through this cell. So that will tell us the potential difference, V. Okay. That is V is equal to V of P minus V of N terminal P and the negative terminal N. So I here is the current flowing from N to P through this cell. So while labeling the current I through the cell, one goes from P to N usually. So then V is equal to epsilon plus IR. So now let us see the Kirchhoff rules. The first rule is junction rule. What is this junction rule? See, at any junction, the sum of the currents entering the junction is equal to the sum of the currents leaving the junction. So this is a very simple rule. This applies equally well if instead of a junction of several lines. See here, if you consider this as a junction A, then here we can write from Kirchhoff's first rule that the sum of the currents entering the junction. So here I3 is entering this junction. So that I3 is equal to sum of the currents leaving the junction, that is I1 plus I2. This is what the first law or the first rule of Kirchhoff says. Okay. See, the proof of this rule, it follows from the fact that when currents are steady, there is no accumulation of charges at any junction or at any point in a line. Thus, the total current flowing in must equal the total current flowing out. So, this is the first rule. Now, the second Kirchhoff's rule. The algebraic sum of charges in potential around any closed loop involving resistors and cells in the loop is 0. Okay, so if you consider these loops, as you can see, they have marked one loop here and the second loop here. So the algebraic summation of this potential around any closed loop will be always equal to 0. If I take I1 into 30 ohm plus 45 volts minus 1 ohm into I3 minus 40 into I3. So this is the potential difference across each resistors in this particular loop. So according to Kirchhoff's second law, the potential difference in this closed loop will be always equal to 0. That is what the second rule of Kirchhoff says. And this second rule, that is loop rule, is also obvious because electric potential is dependent on the location of the point. So thus, starting with any point, if we come back to the same point, obviously the total change must be 0. Potential difference is nothing but the change in potential. So if you start at the same point and if you end at the same point, obviously that difference will be nullified. So in a closed loop, we do come back to the starting point, and hence the rule says that the potential difference in a closed loop is always zero. So this is what the Kirchhoff laws says. The first one is the currents entering the junction, or we can say the sum of the currents entering the junction is equal to the sum of the currents leaving the junction, and the potential difference in a closed loop is always equal to zero.